Ever wonder what CAP, base, solid, and KISS stand for? Let's break down these system design acronyms and see how they help us build better software. The CAP theorem tells us that in any distributed data store, we can only guarantee 2 out of 3 of these properties: consistency, availability, and partition tolerance. Consistency means every read gets the most recent write or returns an error. Availability ensures that every request gets a response, even if it's not the latest data. Partition tolerance means that the system stays operational even when there are network faults. Imagine a distributed database where some servers can't communicate with each other due to network issues, a situation known as network partitioning. If we prioritize consistency, some users might receive errors when accessing the database because not all servers have the latest data. But if we choose availability, every request will get a response, even if it might not reflect the most recent updates. The CAP theorem is often criticized for being too narrow, which brings us to the Pacelc theorem. Pacelc expands on CAP by considering latency as well. It states that if a partition happens, you must choose between availability and consistency, like in CAP. But else, when there's no partition, we still have to choose between latency and consistency. If we use a globally distributed NoSQL database like Amazon DynamoDB, Pacelc forces us to decide whether to prioritize low latency responses over strong consistency. This brings us to a related concept: base. You probably heard of the ACID principles for relational databases, where data needs to be atomic, consistent, isolated, and durable. However, with NoSQL databases, strict consistency isn't always practical, especially in high-performance applications. That's where base comes in. It stands for basically available, soft state, and eventual consistency. Basically available means the system appears available most of the time, even if some parts fail. Soft state implies that data might change over time due to the eventual consistency model. The system does not guarantee immediate consistency, but reaches consistency over time. Eventual consistency means that the database doesn't guarantee that all transactions are seen by all users immediately, but eventually all reads will return the latest value. This allows for high scalability and replication, making it useful in scenarios where a slight delay in consistency is acceptable for faster response times and higher availability. Amazon DynamoDB is a good example of base principles in action. It prioritizes availability and latency for fast responses. Write can be set to eventually consistent or strongly consistent, depending on how strict consistency is needed. While ACID principles are useful for scenarios requiring strong consistency, like financial transactions, base principles shine in large distributed environments where availability and partition tolerance are prioritized. These principles provide more flexibility and resilience for large distributed systems. Let's move on to solid principles, which help us write cleaner, more maintainable code. First up is the single responsibility principle. It states that a class should only have one reason to change. This minimizes the impact of modifications. For example, separating user data management from user notifications ensures that changes in one don't impact the other. Next is the open-close principle. Classes, modules, and functions should be open for extension but closed for modification. We can extend a module's behavior without modifying its source code. It maintains code stability and reduces bugs. For instance, by using an interface for shapes, an area calculator can handle new shapes like circles and rectangles without modifying the core logic. Then there's the Liskov substitution principle. It says that objects of a superclass should be replaceable with objects of the subclasses without affecting the program's correctness. This ensures that a subclass can stand in for a superclass without errors or unexpected behavior. For instance, separating flying behavior from a general bird class ensures that non-flying birds like ostriches won't cause errors. The interface segregation principle states that clients should not be forced to depend upon interfaces they do not use. This encourages creating multiple specific interfaces rather than a single general-purpose interface. It prevents a class from being forced to implement interfaces it doesn't use, reducing the side effect of changes in unrelated interfaces. For example, splitting a worker interface into specific one like workable and eatable, ensures that robot workers aren't forced to implement unnecessary eating methods. Finally, the dependency inversion principle states that high-level modules shouldn't depend on low-level modules. Both should depend on abstractions. This principle aims to reduce the direct dependencies among different modules, making the system easier to modify and extend. For example, introducing a database interface allows a program to work with various databases like MySQL and Postgres without being tightly coupled to any specific implementation. And finally, KISS stands for Keep It Simple, Stupid. It's a principle first used by the U.S. Navy in 1960. In software, it means systems work best when they are simple, both in design and in implementation. Google's search interface is a good example of the KISS principle in action. The interface is famously simple, featuring only a logo, a search box, and a couple of buttons. This simplicity ensures that users are not overwhelmed and can focus on their primary task, searching. The straightforward design minimizes distractions and complications. So next time we design a system, let's remember that the best solutions might not come from adding complexity, but from simplifying our design. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 500,000 readers. Subscribe at blog.bytego.com.